to my today's session, problem solving session on electromagnetic field. Myself, Dr. Sayanti Chatterjee, Associate Professor of Department of Electrical and Electronics Engineering in Hyderabad, IARE College. So today we are going to discuss about the electromagnetic, and our today's outcome is calculate the self-inductance and mutual inductance for different configurations of wires and calculation of the energy stored in the coil. So we will start with a little recap. What is this? What is inductance? We already know that the inductance is directly proportional to the rate of change of electric current flowing through the inductor, and we can write V is equal to L di by dt, where V is the instantaneous voltage. What is L? L is the inductance, its unit is Henry, and di dt is the rate of change of current, and its unit is ampere per second. And what are the types of the inductance? Inductance is basically two types. One is called the self-inductance and another one is called the mutual inductance. Self-inductance means inductance of the coil itself. Due to the current flowing through the coil, the inductance will generate, and this is called the self-inductance. What is mutual inductance? If two coils are in proximity and due to the current in one coil, the flux linkage of the second coil will create or will generate some induction, and this is called the mutual inductance. So already we know the self-inductance of the solenoid. What is solenoid? Solenoid is nothing but the one solenoid is basically one iron bar on which we can connect some coils like this. If small n is the number of turns per unit length, capital N is the total number of turn, and the length of this is L, then we can write as B, the flux density B equals to mu naught Ni. What is N? Number of turns per unit length. Then what is capital N? Total turn. So we can write capital N is equal to small n into small l, where small l is the length of the bar. Next, self-inductance means we know L is equal to N phi by I. And if we put the value, we will get that L is equal to mu n square A by L ampere. So we can tell this is the basic equation of the self-inductance. In here, the important formula is 1, 2 and 3. These three are the important formula which we need later for solving the problem. B is equal to mu naught I, mu naught N into I, or we can write H intensity is equal to N into I, and B is equal to mu naught H. What is the second important formula? Inductance of any coil L is equal to N phi by I, where N is equal to number of turns. And if we put the value, we got mu n square A by L Henry. Next, we will discuss about the self-inductance of the toroid. What is toroid? Toroid is like a disc of the ferromagnetic material on which we are giving some coils, and this is the plus and minus. And here again same thing, N is the number of turns and A is the cross-sectional area. R is the mean radius of the toroid. What is the meaning of mean radius? The radius of the inner circle. So magnetic flux is equal to, we know from the previous, B is equal to mu naught N I by L, where small n number of turns per meter is equal to N by L. Actual formula of B is equal to mu naught N into I. We are substituting the N by capital N by L. So if this is the mean radius of R, so what is the mean length of this? The mean length is L is equal to mean length L is equal to 2 pi R. This is the perimeter of a circle. So L is equal to 2 pi R. So we can write, if capital R is the radius of the outer surface, the inductance we will get is equal to n square mu R square by 2R by H. Where R is equal to, capital R is equal to radius of the outer surface and small r is equal to radius of the inner surface or mean radius. Here also, this is also a very important formula of the inductance calculation. Next important thing is the energy stored. So energy stored is equal to the work done. Already we have discussed. So dW is equal to VI dt, and we are substituting the value of V with L di dt, and we will get inductance is equal to Li square by 2. Inductance is equals to Li square by 2. Or we can write psi square by 2L. What is psi? Psi is nothing but the psi is equal to N into phi. Phi is equal to flux linkage. N is equal to number of turns. And so this is the important formula of this chapter. One is energy is equal to Li square by 2. Another one is equal to W is equal to psi square by 2L. And if some inductance is there, some mutual inductance is there, the total energy W is equal to half L1 if current I1 is flowing in the first conductor and I2 is flowing in the second conductor. We can write W equals to half L1 I1 square plus half L2 I2 square plus minus M12 I1 I2. But here we are taking one assumption that M12 is equal to M21. M21 means mutual inductance of second coil due to the current in first coil, and M12 means mutual inductance of first coil due to the second coil. Let's do the first problem. A solenoid with 300 turns is 300 mm long and 30 mm in diameter. If the current is to 500 mA, calculate the inductance, and number 2, calculate the energy stored in the solenoid. We are assuming the relative permeability mu r equals to 1. So here it is given the diameter. It is given the diameter. What does it mean? The bar is looking like a solid cylinder, and we are giving some connection on it like this. So what is the number of turns? Number of turns is given as 300. What is the diameter given? Diameter is given as 30 millimeter. So what is the cross-sectional area? Cross-sectional area is pi d square by 4. What is the cross-sectional area? Cross-sectional area is pi d square by 4. What is the length? Length is given as 300 millimeter or 0.3. So here we can write pi 30 into 10 to the power minus 3 whole square by 4. We can write like this, or what we can do, we can calculate the radius first. If diameter is 30 millimeter, radius is 15 millimeter, is equal to 15 into 10 to the power minus 3 meter. And in that case, cross-sectional area is pi r square, means pi into 15 into 10 to the power minus 3 square. We can use any of the formula. Length is given. So what is the formula? Already we have discussed the solenoid formula, and it is mu naught n square A by L. So if we put the value, what is the value of mu naught? Mu naught, here it is given mu naught is equal to 1. That's why we are not writing here. So what is mu naught? 4 pi into 10 to the power minus 7 into what is n square? N value is given as 300. A by L. What is A? A we have got pi into 15 into 10 to the power minus 3 whole square divided by L. L is given as 30 millimeter, 0.3. And after the solving this equation, we are getting the unit 2.66 into 10 to the power minus 4 Henry. This is the first part of this problem. Now, if we are going to the second part, what is the second part? Here it is given that mu naught is equal to 4 pi into 10 to the power minus 7. So what is the second part? We are written in red, energy stored in the solenoid. So what is the formula? Half Li square. L value we have got already. We have already calculated the L value. So we will put the value directly. Half L. What is the L value we got? 2.66 into 10 to the power minus 4. And what is the value of I we got? I value is got 500 milliampere. So this is 0.5 ampere. 0.5 square. And after the calculation, we got the value 3.32 into 10 to the power minus 5 and unit is joule. So this is the first problem. Now we are going to the second problem. Two mutually coupled coils are connected in series where L1 is given 0.5 Henry, L2 is given 0.6 Henry and M is given as 0.1 Henry. Current flowing through it is increasing at the rate 1 ampere per second. Derive the expression for voltage induced in coils when they are in series adding connection, when they are in opposite connection. So first we will take the series adding connection. You can see both the current direction is the same direction. And series opposing means both directions are in opposite. So this is called the series opposing direction. So in the series adding direction, total inductance is equal to L1 plus L2 plus 2M. So what is the value of L1? It is given 0.5. L2 is 0.6. H is 0.1. So we are getting the value 1.2. We are getting the value 1.2 Henry. Sorry, it is actually 0.22 M. So it is 0.2. 1.3 Henry. So what is the voltage? We know voltage is equal to L di by dt. Rate of change of volt current is given 1 ampere per second. So we will get 1.3 into 1 is equal to 1.3 volt. If they are in the series opposing, the formula is L1 plus L2 minus 2M. So what is the value? 0.5 plus 0.6 minus 0.2. So it is coming 0.9 Henry. And what is the voltage then? 0.9 into 1 is equal to 0.9 volt. So this is one of the easy problem. Only important thing is the remember the equation of the inductor. Now we are going to the problem number 3. A very long solenoid with 2 into 2 centimeter cross-sectional iron core has 4000 ton. If it carries 500 milliampere current and permeability of iron is 1000 calculate the self-inductance per meter and the energy stored per meter. So here length is not given. So we are thinking the length is 1 meter. So what is the long solenoid? You can see this is the long solenoid. It is mentioned that 2 into 2 centimeter cross section. What does it means? It looks like the cross section. Cross section means if we cut anything in between the middle, it will looks like a small square. So what is this? N is equal to number of turns is equal to 4000. A is equal to cross sectional area. It is given 2 into 2 centimeter square, means we can write 4 centimeter square, or we can write 4 into 10 to the power minus 4 meter square. What is the length? As length is not given, we assumed the length is 1 meter. So again we are using the formula mu naught n square A by L, or we can write mu naught mu R, because here it is in the iron core, mu naught mu R n square A by L. So what is the value of mu naught? Mu naught value we already know, 4 pi into 10 to the power minus 7. What is mu r? Mu r is given as 1000. What is n? N is the number of turns is given as 4000 square, and A is 4 into 10 to the power minus 4 divided by length is not given, means it is 1. And after solving this, we are getting the value 8.042 Henry per meter. So why it is per meter? Because we are assuming the length is in meter. The energy stored in the per meter. So this is the second part. So what is the second part? Second part is the energy stored. So what is the formula of the energy stored? Half L I square. So what is the value? Half L value is 8.042 and I value is given as 500 milliampere square, and we will get the value as 1.0005 joule. Next, problem 4. The mean radius of a toroid is given as 10 centimeter and the number of turns are given 500. If current flowing through it is 0.1 amps, then calculate the magnetic field in Tesla for toroid. No need to calculate the inductance, we only have to calculate the magnetic field. So what is the mean radius is given? Mean radius is given as 10 centimeter. What is the meaning of 10 centimeter? 0.1 meter. What is the number of turns? Number of turns are given is 500. So this is the toroid. Number of turns is given is 500. So we have to calculate the value of the magnetic field. Current is given as 0.1 ampere. So if the radius, the mean radius means smaller. Already we have discussed the mean radius is smaller. So what is the total length? So the total length of this is given as 2 pi into r. R is 0.1. So what is the value of the number of turns per meter? Number of turns per meter is equal to number of turns is total number of turns is given as 5000. Sorry, it is 500 by 2 pi into 0.1. So if we put the value mu, we know h is equal to small n into I. Small n we can calculate from here and I is given as 0.1. And what is B? B is equal to, what is B? B is equal to mu into H. If the value of mu is not given, that's why we wrote mu naught Ni. And if we put the value, we will get the unit 10 to the power minus 4 Tesla. Now we are moving to the problem 5. So what is this? Two identical coils A and B of 1000 tons, both are identical and both has the same number of tons, 1000 tons, each lie in parallel plane such that 80% of the flux produced by one coil links with other. If the current of 5 ampere is flowing, produces a flux 0.05 milliweber, then the flux linking of the B coil, what is the value of the flux linking of the B coil? So there are two coils A and B, and they are near, they are in the proximity, and have the flux linkage. They have the flux linkage of 80%. So you can see from here, this is the one flux, this is the coil 2, and the flux are linking due to the current in the first coil, the current is linking the second coil, and amount of current linking is 80%. Not total current is linking, only 80% current is linking. The current is 5 ampere. It is given, the current value is 5 ampere. So we can write that what is M12, N1 or phi12. Due to current I1, the flux produced is phi1, which links both the coils. So M12 is equal to N1 into phi12. Now, as we know, as total value is not linking, 80% of the flux is linking. So what is the total flux? Total flux is given as 0.05 milliampere. So we can write 80% of the flux produced in the coil 1, and the value is 0.05 milliweber into 0.8, because 80% flux is only linking, and the value is coming as 0.04 milliweber. This problem is very simple. One flux current is flowing in this coil, and it is creating some flux. The 80% of the flux is linking the second one. So if total flux is given 0.5 Weber, 80% means 0.04 Weber. So this is the problem number 5. And this is, you can see, this is the main working principle of the transformer. Flux linking in one coil will add to the second coil. So this is will be the problem number 6, actually, the numbering mistake. Two inductors whose self-inductance are given as 75 millihenry and 55 millihenry respectively are positioned next to each other on a common magnetic core, so that 75% of the lines of flux from first coils are cutting the second coil. Calculate the mutual inductance that exists between these two coils. So what does it mean? See, again, this is the first coil and this is the second coil. N1 is the first coil, and what is the value of the inductance in the first coil? This is 75 millihenry. What is the inductance of the second coil? It is given as the 55 millihenry. And the flux is generating from here and just cutting to the second coil. The flux generating from here is cutting to the second coil. So we can know that the 75% of the flux is cutting from the first coil to second coil, not 100%. Now, what will be the mutual inductance? We know M is equal to K root of L1 L2, where K is known as the mutual coupling. What is the meaning of mutual coupling? The amount of flux, the percentage of flux linking in the second coil, the amount of the flux linking in the second coil, and this value we are assuming as 75%. So we can tell that the 75% of the flux is linking the second coil. So if we put the value 0.75 square root of L1 L2, so 75 millihenry into 55 millihenry, and we are getting the value 48.2 millihenry. So the mutual inductance of this line is 48.2 millihenry. So we are going to our problem number 7. A silicon iron ring of cross-sectional area of 5 cm square has a radial gap of 2 mm cut into it. If the mean length of the silicon iron path is given as 1 centimeter, calculate the magnetomotive force produced of 0.7 milliweber. The H in the iron is given 1650 for 1.4 Tesla. So first you try to understand this problem. This is basically a ring. Ring means it is nothing but a toroid. Where you can see these are the coils on the toroid. So this is plus and this is minus. Now what we are doing? There is the cross-sectional area. What is the meaning of cross-sectional area? A. Cross-sectional area is given as 5 centimeter square. So what is the meaning of 5 centimeter square? We can write 5 into 10 to the power minus 4. 5 into 10 to the power minus 4 meter square. What is the flux? The flux produced phi is equal to 0.7 milliweber. 0.7 milliweber. So we can write 7 into 10 to the power minus 4 Weber. So these two values are given first. First we will think about this. So what is B? B is given as phi by A, total flux by total cross-sectional area. And the phi by A is, if we put the value 7 by 5, we are getting 1.4 ampere turn per meter. What is H? H is given as 1650 for 1.4 Tesla. It is given as 1650 for 1.4 Tesla. And the mean length of this length is given as 0.4 millimeter. The mean length is given as 0.4 millimeter. So what is the total H? Total H is 1650 into 0.4. H is given for per meter. So H for per meter is 1650. So if the length is 0.4, or we can write, L is given as 4 centimeter. So we can write is 0.4 this is actually not given, it is 40 centimeter. So it is the 0.4 meter. We got the H value 660 ampere. 660 ampere is the total MMF. Now we are thinking about the air gap. H value we know. What is the value of this? B is equal to, now what is doing? For the same iron coil, we have cut a small area, we have cut, and this is not there. The ring is looking like this, and this is air, and this radial gap is 2 millimeter. We have to, this radial gap is given as 2 mm. What is the radial gap? So it is the 2 into 10 to the power minus 3 meter. We have to calculate the total H. This is not per meter, we have to calculate the total H. So how to calculate the total H? Total H we can calculate like this. H is equal to, we know, B by mu naught. B value we got. What is the B value? B value is given as 0.7 milliweber. What is the value of mu naught? Mu naught value we know that the H is equal to mu H is equal to B. We are using this formula. What is mu naught value? Mu naught value is 4 pi into 10 to the power minus 7. So putting the value we got, B is equal to 11.1114000 ampere per meter square. So if we want to calculate the intensity within this area, same problem. So H is equal to total H into 0.002. So if we put the value, we can get the MMF. So MMF of this length is 660 ampere. For this small area is 2228 ampere. So total MMF of this ring will be addition of 668 plus 2288. So it is the total MMF of this part. So how to calculate this? Just one quick revision. We know the value of B, flux density, phi by A. So if we are taking that B is equal to 1.4 Tesla for ampere per meter, and for the 1.4 Tesla the H value is 1650. It is given in the problem. So 1650 is for a total closed path. If we are taking the length of 40 centimeter or 0.4 meter, we are getting it as the 660 ampere. Now we are cutting a small radial distance here. So the radial distance is 0.2 millimeter, and we are getting the total value of the MMF of this ring. Now we are going to the problem number 8. Two coils A and B with 800 tons and 1200 tons respectively have a common magnetic circuit. So this is the common magnetic circuit. This means they are not electrically connected, but they are magnetically connected. A current of 0.5 ampere in A will produce a flux of 3 milliweber, and 80% of the flux links with coil B. Calculate the self-inductance and mutual inductance. So first we will calculate the self-inductance. What is the formula of the self-inductance? N1 phi 1 by I1. We know the inductance of the A coil. Inductance of the A coil is N1 phi 1 by I1. Already we discussed this main formula previously. So what is N1 here? N1 of the first coil is 800. What is phi 1? Flux is given as 3 milliweber. 3 milliweber. And what is I1? I1 is given as 0.5. And we are getting the value with 4.8 millihenry. We are getting the value 4.8 millihenry. Next, if we are getting the value, the LB. What is LB? LB is equal to, it depends on the number of turns. And what is the formula? The formula is LB by LA is equal to N2 square or NB square by N1 square. So what is LB? LB is equal to N2 by N1 square into LA. What is N2? N2 is given as, what is N2? N2 is 1200 by 800 square into LA 4.8 millihenry. So after calculating this, we are getting the value 10.8 millihenry. So we got LA and LB. We have to calculate the mutual inductance. So here we can see that the only 80% flux linkage with B. So K value is 0.8 root of L1 plus LB. We will get the value 5.76 millihenry. Here we have one more question. This is not written in this problem. Calculate the, we are just adding one important topic. It is not given. Calculate the energy if current is given 0.5 ampere. So how to calculate the energy? The energy is given as, the total energy is given as half L1 I1 square plus half L2 I2 square, and as both currents are in only one current, we will take it as the plus M I1 I2. Now as the current 0.5 ampere is only flowing, so we can write half L value is 4.8 into, what is the value of I1? I1 value is 0.5 square plus we are going for the second one, half. What is the value of LB? 10.8 into, what is the I2 square? I2 square is given as 0.5 square plus M value is given as 5.76. This is 5.76. I1, I2. In the both case, we are taking the 0.5 into 0.5. So, like this, we can, if we solve this problem, we can get the total energy. We can get the total energy in the section. So, here we have discussed many important problems, and I have one more important problem. In this problem, there is another problem in the question number 6. Actually, I missed. In the question, it is given two coils whose self-inductance are 75 millihenry and 55 millihenry respectively are positioned next to each other. So, for the same problem, if we give it is 100%, what will happen? This is also the another important question of this chapter. If it is 100%, what will happen? If it is 100%, K will be K, the mutual coupling will taken is 1. And this case we are writing is M dash. M dash is equal to 0.75. So it will be 1 into 75 into 55 millihenry. So this is the another important problem of this chapter. So in this chapter we have discussed first what is inductance, what is self-inductance, what is mutual inductance, then one problem from the inductance in a coil, solenoid of a cylinder. Then we have discussed for a square-shaped cylinder, we have solved the problem of the series connection of the two inductors, the problems on toroid, the problems on mutual coupling, and last of all we have discussed the problem of the toroid when it is cut, and the last problem we have discussed about the coils with some turns. So this is the important topic we have discussed in the self-inductance and mutual inductance problem. So thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.